We're going to have to pass on the case histories for a while because we're getting behind and I need to cover the material. But later on we'll take time to go back to some of those case histories. So we're continuing our discussion on flow of water through soil. And last time we saw a number of very important equations. The first one was Q equals VA, where Q is the flow, V is the discharge velocity, and A is the cross-section area through which the water is traveling. We also saw V equals KI, which is Darcy's law. V again is the discharge velocity, K is the soil permeability or hydraulic conductivity, and I is the hydraulic gradient. These are the two main equations. We also have another couple of equations are important. Total head equals elevation head plus pressure head. Elevation head is just how high the point you consider is, and then HP, the pressure head, is UW divided by gamma W. UW being the water pressure or water stress. And then the last one to remember is the hydraulic gradient. And the hydraulic gradient is defined between 2 points. A gradient, it's a slope if you wish. So we define that between 2 points, A and B. And this hydraulic gradient is the ratio of the loss of total head between those 2 points as the water flows from one point to another, divided by the length traveled to go from one point to the other. So it's HTV minus HTA divided by the drainage length LAB. Okay? Very important equations. You need to know those by heart. Very likely to be asked on in the short questions on the midterm. Let me put this one underneath so that I'll have more room. So if we said H sub P equals UW divided by gamma W. All right, and I'll leave those here as long as I can, so you keep them in mind. First thing I want to do is practice through an example these total head, pressure head, elevation head, because they're really fundamentally important. So I'm on page 372. Page 372, and we're going to do together the diagram in figure 13.4.8. Figure 13.4.8. The diagram, so this is a constant head permeameter, like the one you're doing in the lab to measure the permeability. And here is let me reproduce this diagram. So we have a scale, a vertical scale here, that's going to go from 0 to 1.3. So we've got 0 right here, 1.3. So 1 is going to be here, that's 0.5, 0.6, 0.8, 0.4, 0.2, 0.2, 0.4, 0.6, 0.8, 1.2. And we'll need the intermediate graduations like this. So that's the vertical scale, meters if you would. The diagram is a constant head permeameter, and it looks like this. Let's see, it goes from 0 to 0.8. So from 0 to 0.8, I have the permeameter sitting on the table, on the lab table. The soil sample is from 0.1 to 0.7. So 0.1 to 0.7. 0.1 right here. And this is the soil. Now this is water right here. And water is coming out, overflowing on top of the permeameter. The permeameter at the bottom is connected to a container, and this container has water all the way to 1.3 at the top here. So we have a container right here, and the water level is kept at 1.3. Let me erase this to make it clearer. So I have a pipe, a tube, that goes all the way down to here, takes the corner, and is connected to the bottom. So obviously this water level is higher than this, water is going up, having a hard time going to the soil, and finally coming out. And we can measure the flow, Q, cubic meters per second, or whatever convenient units we want. In this permeameter, we're going to identify a number of points. A will be the top of the water. B will be below that. C will be right about here somewhere. D will be below. And E will be here. And the bottom will be F. So understand that this is water. This right here is water. This is water. And this is soil. Connected to C horizontally is a pipe. And this pipe is going to give us the level at which the water is rising in that pipe. And the measurements indicate that at C we are at 0.95. So 0.95 is the level where the water rises in here. Okay? So there is water that rises in the tube all the way to that particular level. Or I should do it in blue for water. Okay? And then we have another pipe connected to D. And at D, the water rises to a different level. It's closer to the height here, so it's going to rise at a higher level. And this one is 1.15. So 1.15. So my pipe is not high enough. I need to extend it like this, and then it rises to 1.15, so right here. So the water rises, I poke through the wall and I connect this tube, and the water rises all the way, it comes to equilibrium right here. So that's the problem, and the question is, draw the head diagrams for this permeameter. So we're going to do a diagram where the heads are going to be plotted. Let's say that this is meters, okay? Elevation in meters. So this scale will have to go in the same distance, 0 to 1.3. So this is 1. And then, so that's going to be 0.5, 6, 8, 4, 2, 1.2, and then 1.3. So this is 0.2, like the other scale, 0.6, 0.8, 1, 1.2. Okay, so heads in meters. And we're going to need, again, intermediate graduations. 1, 2, 3, 4, 5, 6, and 1.3 at the very top. Okay, the question is, draw the diagrams for elevation head, for pressure head, and for total head. We're going to do that. The easiest is elevation head, because it's simply the height above the datum, above zero. And we're going to create a table, if you wish, that will have the points, so A, B, C, D, E, and F. And then for each one of those, we're going to give the elevation head, the pressure head, and the total head. Okay, so we're forming a table. And we're going to fill that table for each one of those quantities. All right, so let's start. As I said, the elevation head is the easiest. So elevation head is at F is going to be 0. Elevation head at E is going to be 0.1. At D, let's see, what did I choose? Well, unfortunately, D was 0.3. All right, so we'll keep it according to the book. I should have put D a little bit lower here. At C, it is 0.5. When I look at the diagram of the book, so the C and D are a little bit higher. And then at B, we are at 0.7. Okay, that's correct. Again, all I'm doing is looking across and reading this number here on the vertical scale. And A is at 0.8. All right, done. We've got elevation head everywhere. Pressure head. Remember last time I said if you want to know the pressure head, you have to think of a pipe that is connected to the point where you want the pressure head. And that this pressure head is the water pressure divided by gamma W. So if you have a pipe, a standpipe connected to that point, you just look where the water rises, and this minus that is the pressure head. The key is to have such a pipe. And in dams, we don't have often those kinds of pipes. So we'll have to find another way to do it. But here, we do have these pipes. So the problem is a bit easier in that sense. Let's look at the pressure head at F. Do you see a pipe connected to F where we have free water in the pipe, no soil? Well, at F, if I go this way, this is free water all the way to here. So the pressure head at F is going to be 1.3. Pressure head, 1.3. At E, well, at E, I also have a continuous water path all the way to a free water level here. And the pressure head at E will be the difference in level between this level and that level. Because remember, it's the difference between where the water level is and the point that you consider. That distance is the pressure head. So at F, we went all the way up here. The difference was 1.3. At E, I can still go this way, and I get now 1.3 minus 0.1, I get 1.2. So at E, the pressure head is 1.2. You might say, well, why didn't you go from E all the way to here? Because I have to go through soil here. And that does not give me the pressure head. So in any of those cases, I've got to find a free water path, meaning there is no soil in the way. It's just a pipe that has only water, and that gives me the pressure head. So let's do D now. Well, at D, you see I have this pipe here. And this pipe goes up to this level. And this level is 1.15. And D was at 0.3. So the pressure head at D is going to be 1.15 minus 0.3, so that's 0.85. At C, well, again, I have this, we call them piezometers or manometers, stand pipes. We have this stand pipe here, and the water level rises to here, which was 0.95, I believe. The drawing, well, it's 0.95, it looks like in here. Yeah, we're 0.95. So 0.95, and then this was, the elevation head at C was 0.5. So 0.95 minus 0.5, I got 0.45 as the pressure head at C. Again, I couldn't go this way because I had to go through soil. So I was actually losing energy here, but here I've got a sandpipe. I'm back to a static condition, if you wish. So then I just have the hydrostatic pressure. Then at B, now I'm through water only at B here, and therefore the pressure head at B is just 0.1. Difference between A and B. And then at A, I've got 0. These are the pressure heads. And then now, I simply add the two to get the total head, because total head is elevation head plus pressure head. So I've got 1.3, 1.3, 1.15, 0.95, 0.8, and 0.8. And remember that the total head is proportional to the energy spent by the water. So the water starts at F. It's got plenty of energy because there's a lot of pressure behind it that's helping it go up the sample. So at F, we have 1.3 meters of total head measuring this energy. At E, we also have 1.3. Why? Because the water hasn't spent any energy to drive from F to E, because there is nothing in the way. But then it starts losing energy when it goes from E to D to C to B, because it has to drive through the soil and there's friction. We talked about the seepage force before. And you can see it here. It loses energy, 1.15, 0.95, 0.8. And from B to A, it doesn't lose energy because there's nothing in the way. So 0.8 and then 0.8. So from this, we can draw the diagrams, the head diagrams, and let's see, so the elevation head goes to 8. So at 0.8, I've got 0.8. Okay, so basically, the elevation head is a straight line, diagonal, because the elevation head is the elevation. All right. So that's the first diagram for the elevation head. And then we're going to do the pressure head. So the pressure head was in blue. At A, I've got 0. So at this point, at A, I've got 0. 0 pressure head. And then at B, I've got 0.1. So at B, I've got 0.1 right here. And then at C, and again, C was at 0.5. My diagram is not quite right. So I've got 0.45. So I'm right here at C. And then at D, I've got 0.85. And D was at 0.3. 0.85 is right here. And then at, where am I? D, C, D, E. At E, I've got 1.2. And E was right here, 1.2. Right there. And then at F, I've got 1.2. Okay? So the diagram for the pressure head is like this. Okay? So this is H sub P. And this one was H sub E. And then the total head is the addition of these two. So I've got to, let's see, I can start at F. So I've got 1.3, and I've got 1.3 also at E. So the diagram is vertical. And then at D, I've got 1.15. So D was 0.3 across 1.15, I'm right here. And then at C, I've got, C was at 0.5, I've got 0.95. So 0.95 is right here, 0.95. At B, I have, where is B? 0.8. At B, so B was at 0.7. I've got 0.8 right here. And then at A, I have 0.8 as well. So total head, total head, total head, total head, total head. Okay? So that's the diagram of the total head. So I hope all this helps you to understand and to calculate or to obtain elevation head, pressure head, and total head. When we deal with dams or excavations, you know, we have water flowing into an excavation or a cofferdam or something like this, we often do not have these standpipes connected, and so we don't know the pressure head. And so you see in this case we went elevation head, pressure head, and total head. But in the general case, when we deal with those three-dimensional problems, we will go elevation head, total head, and then by difference we will get the pressure head. And the solution to the total head is where we need to use flow nets, and which are a graphical solution to the governing differential equation. So we will look at this next time, but at least this example gives you a good sense of what these heads are and how they behave. And you can see that obviously the pressure in the pressure is increasing as you go deeper, but the pressure at F, you know, we've seen when we did the effective stress calculation, and we had a certain depth below groundwater level, and we said it's that depth times the unit width of water. This is not the case. You cannot apply this. Why? Because here the water is moving. And in the previous case where we had the soil and the groundwater level, everything was not moving. It was static. Well, in that case, when it's static, you can go from the point to the groundwater level and say that's the height of water, and therefore I've got hydrostatic water pressure at the bottom. Here we have hydrodynamic water pressure, and you cannot go distance from F to A times gamma W. You have to do that. You have to find a clear water path to a water level. That's why the pressure at F is this much and not that much, because the water loses a lot of energy to go through the soil. All right, so that's what I wanted to do for this part. Now we need to turn to how do we measure this all-important property right here, K. Because you can see that Q equals VA, V equals KI, these quantities, we typically can calculate them. But the K is soil specific, and soils vary all over the place. So we have to find a way to measure this K value, and we do that in the lab, and we do that in the field. Early in the course I said, we have lab tests, we have field tests. And they're both very valuable, and a balanced soil investigation makes use of some lab tests and some field tests. So let's see how we can measure this K value. And K varies dramatically. You can imagine that the difference between a gravel and a clay will be very large in terms of how fast the water goes through. Because if you think of this, Darcy's law here, V equals Ki. And I told you I does vary, but it has no units. Length divided by length. So I has no units. So units of K will be the units of V, meters per second. But meters per second, the water is definitely not going at very high speed in the soil. So we're going to be looking at numbers that are 10 to the minus 2 to 10 to the minus 10 meters per second. So it's going nowhere fast, but it is going. And you saw the Teton Dam, it is going. And it can do some significant damage. All right, so how do we measure? And we don't have the same test because K varies so much. And I'll write it here. K varies from K in soils, varies from 10 to the minus 1 meter per second to 10 to the minus 11 meters per second. So 10 minus 11 meter per second, I don't know, it's a few centimeters per year. Or it's not going very fast. So we don't have the same test, and this would be like sand and gravel at one end, and this would be silts and clays at the other. So typically, we make a distinction between the test we use for sand and gravel and the test we use for silts and clays. The one you're doing in the lab is for sand and gravel because it's a much simpler test, and we will start with this one. It is called the constant head permeability. And that's the one that Darcy used when he was asked about the problem in Dijon, where they were losing water in the fountains, and he had to find out where the water was going so he could fix the problem. And that's when he developed that very useful constitutive law. So the constant head permeameter is actually the one that we just talked about, where you have a soil sample, and I'll simplify the device, and you have a bucket here, you have the water. So this is kept constant. So the head at any point in the soil sample, so this is the soil sample. So the head anywhere in the sample is constant. It's not the same, it varies, the head varies, because you know, right here the water is coming out. And you're measuring the flow Q. So this is cubic meters per second. Very, very small, okay? And we keep that distance constant. You can, doing the same thing we did just on this exercise, you can see that the difference in total head between A and B is delta HT AB is this difference right here. That's the difference in total head between A and B. You could calculate it looking at back at the problem that we just finished. The length traveled from A to B is this length right here, L. That's the length of the sample. So if you write the equations that you have, and that is Q equals VA, A being the cross-section of the sample, so pi, let's say that the sample has a diameter D, A would be pi d squared over 4, and V would be the discharge velocity. Remember the distinction between seepage velocity and discharge velocity? Seepage is the velocity of the water molecule on the speedometer, and V discharge is the one associated with the total area. So we write Q equals VA, and then we write V equals KI. I from A to B for the whole sample, because that's what we're interested in, is going to be delta HT AB divided by L. And so if you regroup everything, you're going to have, because you're measuring Q, you're measuring delta HT, L, Q, and then you know the diameter D, so you have in the end Q equals V, that's KI times A, and I is equal to delta HT, I'll drop the AB, this is the length AB, over L times A, and so therefore K is equal to Q times L over A delta HT. Okay? So that's how you get the permeability of the soil. Meter cubed per second, meter, meter square, meter. So you end up with meter per second as the units of K. This is used for sand and gravel. And K values here are typically 10 to the minus 1 to 10 to the minus 6 meters per second, something like that. Okay? Constant head per diameter, we use that for sand and gravel. Now, if you imagine that this now is clay, and you're setting up your thing, and you're waiting here with the beaker for Q, and drip, drip, drip. You'd wait a long time before you get in a sizable volume, and the evaporation may actually mess up your measurement. So you wouldn't be able to have very accurate measurement. To remedy this situation, we use what is called the falling head permeameter. So let's talk about the falling head permeameter. So this device is used for silts and clays. How does it work? The setup is different. The setup is like this. You have a tiny tube, and then you have the soil sample, the same tiny tube, and you get in here in a bucket of water. Okay? So soil sample is here. And this is water. There's a water level here, and there's water level here. So the water is actually falling down, coming down as a function of time, and percolating or traveling through, seeping through the soil. And because the tube is so tiny in diameter, a little bit of water seeping through the soil shows up as a measurable drop in water level. So let's say that the area here in the tiny tube is little a, and then the area in the sample is capital A. And we're going to and the length of the sample is L. So this is L. We have the water level right here. So the total head is the difference between this point and that point. And you can do the calculations, go through what we just did. So here, you would have the total head. But now this total head would be at a time t, because the water is coming down. So the total head starts at time t equals 0, at t equals 0, you're going to have H0. And then at t equals t sub 1, let's say, 10 minutes. Then at this point, we're going to have a lower value, and we're going to call that H1. So during the test, you have the time watch. You start the time, and you record that height, and the water goes down, goes down, goes down. 10 minutes later, click, you record T1, and you record this level. So you measure H0, you measure H1, you have L, you measure the area here, and you have the area of the tube. So what is the expression to obtain K from this test? So maybe it's a little bit more complicated, but not that much. And we write the same types of equation because that's all we have. So first of all, remember we have Q equals VA. We have V equals KI, and we have I equals loss of total head. So I is going to be the loss of total head, which is H. So the total head, the water level is here before the flow, water level is here after the flow, loss of total head is H. And H is a function of T, divided by the length of the sample, because that's the distance traveled. we also know that Q, the flow, we can estimate, we can measure the flow by how much the level of water is dropping in the tiny tube at the top. So this one is going to be A times the drop, which will be dH, and then divided by dt, because the volume is HDH, the area times the elemental drop of water level as a function of time. And then I got to put a minus in here because dH is negative. So for the flow to be positive, I got to put a minus in here. So if I regroup these equations, then I get VA, which is KIA. So I've got KIA, big A, because that's the soil area, equal minus A dH dt. But I is H over L. So then I go back here and I put K H over L, capital A equals minus A dH dt. So that's a differential equation. I've got to solve it. So dt equal, dt goes here. So I've got minus A L over K capital A. And then what's left is dH over H. And so I've got to integrate this, and the integral of dt will be from 0 to t1, and the integral for h will be from h0 to h1. So then I've got t1 minus 0, so t1 equals minus AL over KA. This is natural log, so I got natural log of H1 minus natural log of H0. So natural log of H1 minus natural log of H0. So the difference in logs will be the ratio. And I've got, and if I flip them around, I'm going to have T1 equals AL over K capital A, natural log of H0 over H1. And if I want it in decimal log, because this is the Neperian or natural log, then that would be 2.3. That's the ratio with the natural log for the decimal log. AL KA decimal log of H0 over H1. And then I can take K out of that. So what does that give me? Well, the same thing. T1 goes in there. 2.3 AL T1 LA log of H0 over H1. Okay, and that's the equation for obtaining the hydraulic conductivity, the permeability. No dimension. The A are the same dimension. L over T meters per second. Okay, so it's consistent in units. Well, that's how we measure this. And as I said, this is for silts and clays. And so we're talking about K values that are in the range of 10 to the minus 7 to 10 to the minus 11 meters per second. A very, very tiny flow. Having said all this, these are lab tests. we also run field tests. And these field tests, there are a number of them. And the one I like is one that's relatively simple, and it's called the pumping test. So field pumping test. And the way that test works is you drill a hole in the ground, you go to the site, and you pump water out of the hole. So it goes like this. Here's the site. You drill a hole, and as you know, if you go to a site, you're going to find water at some level. And this is the groundwater level. So before you start pumping, you have a groundwater level. And so the water level is here in the borehole. If you start pumping at a rate Q, then the water is going to go down in the hole, and let's say that the hole goes down to here, and the water is going to go down to here. So instead of being here, you bring it down here, and you keep pumping so that you keep this level constant. And then you can see that after a while, now it takes a little bit of time. The water level will be depressed to match this level, which you maintain constant. So right here, pump to keep this level constant. Okay. When you do that, you get Q. And then the measurements you make are at two different radii. So you make another hole in the ground here, and another hole in the ground right here. And the measurements that you make, by the way, this test is described, let's see, somewhere. I made a note here. Field tests, 13.6, is that what it is? Let's see, 128, page 128. 128, here we go. So the pumping test, so let's say that we'll be bringing it down here, and we have an impervious layer at some depth right here. So this is right here, impervious. Okay? And you measure the height from the impervious layer in this boring. You drill, there's a hole here, all the way to there, a hole all the way to there. And the distance is R1. Let's see, which one did I take? R1 was the closest one. So this distance here is R1. And this distance here is R2. And then this height from here to there is H2, corresponding to R2. And this height here is H1, corresponding to R1. And then, we go through a derivation like this one, and the equation is, here we are, K equal, I'll put it here, K equal Q log R2 over R1. Is this a natural log? Yes. So this is a natural log R2 over R1 divided by pi H2 squared minus H1 squared. Okay? So that's the equation for K. For the field pumping test. And this is a test that's more appropriate for coarser materials, because you can imagine if you have to pump and you just get drip drip in the hole, well, that it's going to be difficult to pump accurately. So this tends to be for soils that are coarser material. But that brings the final point when we deal with these sorts of measurements. We tend to, so we'll take samples and we'll bring them back to the lab and we'll make some measurements in the field, in the lab. And then we go to the field and we make some other measurements of the same quantity, the permeability. And if I plot here, now I'm looking at figure 13.6 on page 373. And if I have K, the permeability, so K meters per second, divided to K large scale, if you wish. And the reason I do this is because when you test soils in the lab, this is a small piece of soil. When you test soils in the field, this is a huge area. And so the features that are at a larger scale, like fractures, joint fissures, micro cracks, are not included when you make those measurements. So the tendency is to find that the measurements in the lab are a lot smaller. This might be 10 to the minus 3, this ratio, all the way to 10 to the 0, which is 1. And then this is the volume of soil tested increasing. So you can imagine that the lab tests are going to be here and the field tests are going to be there. And when you look at the data, you would find that there is a tremendous difference between the tests done in the lab, because the lab scale is right here, and in the field. So be very careful with this, that when you measure things, for example, and I'll stop here, oops, I'm over time. If you test a landfill liner, and you do some tests, and you say, oh my goodness, no water will ever go through this liner. But you build it at the large scale, and there may be some cracks. And you find out that when you run those field tests, you have a much higher permeability that doesn't pass the specification. So be careful and keep in mind that field scale permeability is a lot higher than lab scale permeability. All right, thank you. We will see you next time.